Okay, related rates. I'm going to take a couple problems out of the textbook. These are all out of the textbook. I'll put numbers by them so you can refer to these in the textbook if you want to. But these are good examples. Can you quiet, please? These are good examples of what I would call advanced related rates problems, where these are a little bit, they're not, we've looked at a couple, but they've been sort of introductory kinds of, spherical balloons growing, things like that. Now we're going to look at some that are just a little bit more complicated to set up. Same idea though. Okay, so let's look at number 21 in the textbook. So number 21 in the textbook. Yeah, on what page? Yeah, we have textbook. It's on page 146. Hey. Okay, I'll write it down. 21 in the textbook says, does everybody have, do I need to write it down? Probably not a lot of people have textbook.
I thought it was like a plant that was made of sand. Sexual. That's interesting. It's kind of long. Conical?
Mr. Hoyle, what's the second to last word in the second line?
Conical.
Okay.
Yeah.
You're welcome.
Oh, yeah.
Yeah, I know.
Okay, I'm done my.
Okay, so there's our problem. So we've got sand falling off this conveyor belt. It's falling onto this conical pile that just keeps growing. The nature of the sand is such that the conical pile has a specific shape. It's always, the diameter is always 3 times the height or the altitude. We know that the stuff is falling off or it's being added to the pile at a rate of 10 cubic feet per minute. And we're wanting to know at what rate is the height of the pile changing when the pile is 15 feet high. That's pretty cool that we're going to be able to do that. So let's look at this like just any other related rate problem. So what are the steps we go through to solve a related rate problem? What do we do first? Well, not yet. Not yet. Before we do anything,
Write down what we know.
we gotta write down, exactly, we have to write down the stuff that we know and what we're trying to find, and if it's useful, we'll draw ourselves a little picture. So let's look at a picture. Our picture is just gonna be the cross-section of the pile is all we really need. It's not like it's super helpful, but I think it's just good to have up there. So our picture just looks like that, right? Okay, and this is the height or the altitude, and the diameter of the base. This is the radius of the base, right?
I don't know.
Okay? I mean, if we're just looking in cross-section at this cone, okay?
Yep.
You bet. Okay, so now, what is the stuff that we're given, first of all? You were looking for the numbers, right?
Rate, not rate.
Okay, there's a rate, so there's something important right there. Sand is falling onto the pile at a rate of 10 cubic feet per minute. So somebody raise your hand and tell me, what is that?
It's a rate.
It's a rate, okay, but what rate? I wanna know, what am I gonna label that?
Initial
Time.
volume.
That's what we want.
Okay, it's gonna be a rate, isn't it, right? So it's a derivative, right? It's a rate, because it's a ratio, right? It's got time on the bottom. But what is changing with time? Look at the units. The units are what help us here.
The feet.
Okay, but it's not feet.
No, minutes.
It's cubic feet. Cubic feet is a measure of what? Volume. Okay, so isn't that just V dot then,
Yeah.
right? So V dot is positive 10 in whatever units we're using. Our units are, we're using feet for our linear measurement and minutes for our time, right? Okay. So V dot equals 10, right? There's one thing. What else do we know here? Well, we know the diameter of the cone is 3 times the altitude. That'll be useful to us, but that's really not a quantity. That's not a snapshot value, is it? The snapshot values are the values of either the rates or the quantities that are changing, right? So what else do they tell us? Okay, H is 15, right? And what are we trying to find?
The rate.
Rate of change of what? Height. So what's that gonna be?
Height.
H dot. Good. Okay, so then, we're not given that much, right? So there's our stuff. Now what's next? Okay, right, now we want the parent equation. Now we just blur our vision and ignore the dots. So what kinds of quantities are we relating here? Okay, but feet, you're sure that we might measure them in units of feet, but what are the quantities that are being related? Volume and height, okay? For what kind of an object? What kind of a thing? A cone. So then we want to come up with the parent equation is the equation that relates volume to the height of a cone, right? So what is then the parent equation for a cone? Anybody remember? It's 1/3 pi r squared height. So yeah, it's
Close enough.
1/3 base times, that's what it is, 1/3 base times height. Base is pi r squared, right? Okay? Okay, what about that looks a little problematic?
Everything.
Variables.
Just everything.
Everything?
Yes.
Tons of variables.
Okay, lots of variables. Right, lots of variables. So we've got a V, we've got an R, and we've got an H, right? I mean, I wouldn't say problematic, but you look at it and you think, okay, well, that's makes it a little bit harder, right? Because we've got 2 independent variables and 1 dependent variable, so 3 variables total. Look at the information that we're given here. Are we given anything about R?
No.
Yes.
Well, okay, indirectly, yeah, we are. We're not given any direct information in terms of what the value of R or R dot is, but we're given some information about how R is related to H. Yes, sir?
R will always be 1/3 of H.
R, almost something like that. The diameter is, well, we can get down, it's something like, we'll get to the specifics in a moment. But we can relate R to H by that given information, right? You know, this is a really important problem to look at because there's a lot of dead ends we could take that make the problem a little bit harder. And I think that's one of the hardest things to develop as a math student is the ability to kind of look ahead and see, okay, now, how can I plan this in a way where it's going to be efficient and easy, right? So let's take this parent equation and let's go to the next page and let's just do some calculus. Let's do our implicit differentiation to relate the rates, okay?
So V dot.
Okay, so if we implicitly differentiate with respect to time, first of all, you already identified this, but just state it again. What are the variables there? R, H, and V. Those are all things we would expect to change, right? So if we differentiate, what do we get? Equals, we'll call that just pi over 3, how about? Times what?
R squared H. No, R squared
R squared H dot, good, plus,
H, 2 times 2R.
okay, so 2RH
And then R dot, well,
R dot. Everybody see that?
How?
Because we've got H times the derivative of R squared, which is 2R R dot.
Mr. Oya,
Yep.
why did we do it again?
Say it again.
Is it because we just had that initially? that
Well,
we were doing
what
it?
what is this right here? That's a product. So we have to use product, yeah.
Yeah, I understand that it's the product what we're using, I'm just wondering why we were doing the derivative, is it because the derivative is what we've been given?
Well, because we're doing the derivative because look what the question's asking for. It's asking for H dot, and we're given a V dot,
So
right?
it's just because they asked us for a derivative.
Right, right. So this is not a boring, algebra problem from past classes where nothing's changing. This is a calculus problem, which is dynamic. Things are changing. And so we're going to take this original relationship between the various parts of a cone, right? Parameters of a cone, and we're going to calculusify this. We're going to differentiate it and make it and introduce these rates. And so now this becomes more interesting. Now this is telling us about how the rates are related to each other, the rates of change of these quantities. That's what calculus is concerned with, right? It's things that change. So what do we do here then? We're trying to solve for H dot, right? Okay, yeah, we're gonna have to do some substituting and maybe some isolating, right? But before we do this, let's look at this a little bit here. When I solve for H dot, and we can do that, that's fine. I can solve for H dot. What is my answer going to be written in terms of?
R dot.
I'm gonna get V dot, so I'm gonna get R dot, I'm gonna get R and H, okay? So that's, how are we gonna deal with that? If we go back to our list of snapshot variables, we're missing two important things there. We're missing R's and R dots.
Yeah.
So what could we do?
What about the 3 times?
Okay, yeah, there's some important information. This stuff right here where it tells us that the diameter of the cone is 3 times the altitude. Okay, what's that say? Diameter is equal to 2R, right? So that tells us that 2R equals 3H, right? Does that make sense?
Yes, I get
How do we know
but why is it 2?
Yeah.
Well, because that's diameter.
Yeah, but how do you know the diameter?
is like the full
Diameter is radius.
radius is
Oh, yes, right.
Right?
half of the diameter.
Wow.
Right? Okay, so diameter is just twice the radius.
Yeah.
So we come up with this equation. Now, if we solve this for R, we don't even really have to solve it for R. Well, we do eventually. If I implicitly differentiate both sides of this equation, because I also need to get an R dot, don't I?
Yeah.
Okay, what do we end up getting?
R, 2R.
Equals 3H.
2 equals 3.
I heard it, 2R dot, right?
Oh, I see.
Equals,
Oh, 3H dot.
okay, so those tell us something important. Those tell us if we want to know what the value of R is, well, we can find it because R is just equal to 3/2 H, and R dot is just equal to 3/2 H dot, right? So we could add some extra information here to our, we could add some extra information to our snapshot value chart, couldn't we? Right? If the height is 15, then what's the radius going to be?
15 times 3 over half.
Yeah, so it's going to be 45 halves,
Yeah.
right?
But we're trying to find H dot, is that what we're trying to?
Yeah,
Okay.
we're trying to find H dot. Okay, but the problem here is we don't really know what R dot is, do we?
But.
Right.
Wait, why is R?
Why do we don't know what H dot is?
Right, we don't know what H dot is.
Oh.
Okay, good. But we could do a substitution, right? We know that
We get 2H
R dot
dots.
has to be equal to 3/2 H dot, don't we? Right? So if we go back to our other equation over here, we could say, okay, this R dot we could deal with. That R dot has got to be equal to 3/2 H dot,
So smart.
right? Yeah.
Sorry,
happens to the R's? Oh, we have R.
Well, the R we could plug in values. If we go back, what was R was 45 halves. Okay, so we could plug in 45 halves into that R and that R, right? We know the value of H, right? We know the value of V dot, and we could replace this R dot with a 3/2 H dot, and we're really just trying to solve for H dot, right?
Okay, I get that.
Okay, now, we could do all this stuff. That seems like a lot of work, doesn't it?
Yeah.
I mean, it's, reasonable amount. Can somebody tell me how maybe we could have been a little smarter about this? Where did the complexity of this problem come from?
Doing the isolate X or
Then when
H
you did the
first.
derivative
You know,
of volume.
and take your derivative.
Uh,
You don't have to do the product.
okay,
No, but-
okay, well, I
Like
mean,
substitute before you take the derivative?
there you go. That's it. Say that again. We're going to, listen everybody, this is the secret. What are we gonna do, Alexis?
Substitute before you take the derivative.
Yeah. The complexity came from the fact that we had two variables here, right? So we had a product rule. That's what created all these different kinds of quantities that we've got to substitute for, right? It made the problem much harder. Wouldn't it have been much easier in a way if we could have just eliminated a variable from the beginning?
Yeah.
We can, right? Because we know the relationship. We know that R equals 3/2 H, right? And we have information about H already. So that would have been a better deal. So let's do that. Let's go to the next page and let's just abandon that and do it this way instead. So we know V equals
So just X it out.
pi over 3 R squared H, and we found 2 pages back that R equals 3/2 H, right? That was wasn't that right?
Yeah. No.
No.
Yeah.
Oh, that's right, yeah.
But it's 45 halves because it's.
Yeah,
Three
when you
times, that's
substitute
right,
H.
yeah, there we go. Okay, so R equals 3/2 H, so let's make this substitution. So let's just substitute right there, and then what are we gonna get? V equals, well, that's terrible, why? I get so excited about this, I just wanna write real fast.
Yeah, why?
Pi over 2 squared.
That's just before we solve it.
Pi over 3 times the quantity, 3H over 2 squared times H, right?
Why?
Because I'm squaring my 3/2 H.
Why don't we take? Yeah, that's why.
Okay, good question.
If we hadn't solved for it.
Now, the question was, it's an excellent question, there's a very good answer to this too. Why can't we make it 45 halves first? Okay, because you can never in calculus, you can never plug in the value of a derivative or a quantity until after you differentiate. Because what is the derivative of a constant always equal to? Zero. So if I were to plug in a number for a variable here and I differentiate, the math gods are gonna think that that's a constant and they're gonna give us back a value of 0 for the derivative, which is not right, because it's a variable, right? So we can never plug and chug until after we've done the calculus, right? Okay? Everybody's okay with this then?
Yeah.
We just made a substitution, now we'll simplify. Well, that's no big deal, we're gonna square out this fraction so we get 9h squared over 4,
Yeah.
right? And then the 9 over 3 will reduce to just a 3 on top. So when all the dust settles, we just get V equals pi H
Square.
cubed, because I got it right, over 4. Oh, 3. I get that, right?
No, I think it'd just be over 4.
What?
Where's the,
Yeah.
why
Can
not
we
over?
just
I
do it?
don't think it's
Okay.
3, is it?
Yeah, well, let's just go through it.
Yeah.
What
I
happens
think
to the?
I thought
There's
they,
9.
oh, okay, so then, yeah. 'cause you
Right.
squared
I don't
it.
understand how you got 3 right
Yeah, no, you did.
there. Pi and then.
So when I-
H squared over.
So I can do this, right?
Yeah.
Okay, so then I get 3 pi over 4 times H cubed. Okay, much better. That's a much, much better parent equation, isn't it?
Yeah.
Now when we differentiate, this is no big deal. If we take the derivative of this one,
Why isn't the form?
well, it could be.
Just 6.
It could be. I just pulled the variable. This is our constant. I just pulled the variable out by itself. So then V dot equals what?
Would be 6 pi,
not 6.
oh, not, yeah, 9
Nine.
pi or 8 squared H dot.
Good,
Each square.
right?
How'd you get that?
Nice job.
So we just got our constant out front times 3 is right there. H squared, and then I have to differentiate the H with respect to T, which gives me my H dot. So it's a chain rule problem. Because we're not differentiating with respect to H, we're differentiating with respect to T. Right? So, right, so now we're trying, the question asked us for H dot, didn't it?
Yeah.
So we'll solve for H dot. So H dot would equal what? We're gonna get,
10.
I'm gonna multiply by the reciprocal of this, so I'm gonna get 4 V dot over 9 pi H squared. Right?
Can you just plug in?
Well, you
and
could,
have one?
sure, but I mean, I like to solve for the variable first and then plug in because variables are easier to write than big numbers. But
Could you,
there's no reason you couldn't. Right?
Wait, why is the, okay.
Make sense? All we did was we just algebraically isolated that, right? Okay, now we'll plug in Chuck. Plug in the values. Do you remember the values?
Yeah.
yeah, 4 times 10,
And it was 10 cubic feet per minute, right?
yeah.
We'll go ahead and put units in. So we can show that they work. Over
9 pi 15 squared.
9 times pi times 15 feet squared. Okay, so
I got it is 125.
is
No.
225.
225. So close. So close.
Yeah, by 100. That's
I
not big.
tried.
Well, cause that's what one is 11.
Well, it's 8 over 405 pi.
8, okay, thank you.
I already did that in my head.
There's a glitch.
So it's 8 over 405 pi. Now what, if we simplify it, what are the units gonna be? I'm gonna get cubic feet per minute divided by feet squared, yeah, so it's gonna be feet per minute, which are the right units, aren't they? So the height of the cone is increasing at a rate of, a very small rate, 8 over 405 pi feet per minute. Okay? That's our answer.
That was really Is that like grain by grain? Like coming down every 5 seconds?
Well, think about what's happening with that. The sand is kind of cascading down the sides, right?
Yeah.
How did we flip the 4 and the 9?
Thank you.
How did we flip the 4 and the 9?
It's a reciprocal to get it to
It
the
was
other
multiplied
side.
by the reciprocal to get rid of that,
You don't make
right?
it
So that put the 4 on top, the 9 pi on the bottom. I'm gonna divide or multiply by 1 over 8 squared. So that goes to the bottom, right?
It's anything necessary.
Okay, real quick, this will help with your algebra a little bit. Would you agree if we're solving for H dot here, this is just a product, right? These are all just factors, right? So if I want to move the factors, all this stuff that's being multiplied and divided by H bar, right? If I want to get rid of that, everything that's on the top is just going to end up on the bottom, right? Because I'm going to divide those away. Everything on the bottom is going to end up on top because I'm going to multiply to undo those, right? So all this stuff, here's a way to think about this that makes it a little easier. All this stuff is in the numerator, so it's got to end up in the denominator of the other side. And this guy right here was in the denominator, so it's going to end up in the numerator with what was already in the numerator on that side, right? You see how you can kind of conceptualize the algebra there a little bit? Right, because you undo multiplication by division, you undo division by multiplication. So when you move these to the other side of the equation, they just have to flip-flop, right? Okay. It would have been more complicated if we were adding and subtracting things, but we weren't, right? Okay? Make sense? Let's go back and just real quick look at what we did. That's, what we did was Really, I mean, and I can't emphasize enough how important it was that we substituted first, right? That was huge, because it eliminated a variable in favor of the stuff that we knew about and we're trying to find. We didn't have any information about ours. Even if we did, I would still do it this way because it's so much easier, right? The derivative was not a product rule derivative, it was just a regular old power rule derivative, much easier. So we took this information, we used this secondary relationship, right, between R and H to substitute and eliminate a variable, and then we just took our parent equation, differentiated, and plugged in Chug. Yep.
So like for you, when you see that problem, did you know like immediately that we were gonna go down that route, or did it take you like going through the steps to figure out that that would be the easiest way?
Honestly, no, I saw that. Because I saw that I knew, I mean, if you just kind of think about this, not in all the details, but the way I would think about this is, okay, I know the volume of a cone has to depend on radius and height. So there's two variables. And I'm given some information right here. This just, to me, that said, okay, that's good. Because now I can relate R and H. And so I can always solve for one in terms of the other and make a substitution. So I can eliminate one.
So you knew it was gonna be a product. Right?
Yeah, I mean, I kind of,
Or it
and
was
you
gonna
will
be
too. I just kind of knew, okay, there's going to be a way for me to eliminate a variable that's going to make this easier, right? And that's kind of, I mean, and that you will too, next time or the time after that or something.
Will it always work out so we can substitute like that with it? Will they give us the information that?
No, I'm not going to say that, but when they do, take advantage of it. Yeah. Okay. All right. So. I wanted to look at something. Oh yeah, this is a really good one. How much time do we have? 13 minutes. Okay, that one's gonna take too long. I'm gonna do a different one then. This is a really cool.
This number problem.
Okay, let's do 37. I think is what I really like. Oh, yeah, this is such a good one. Okay.
Mr. Ray, can I go to the bathroom so
Yep.
fast?
Which number is this?
This is number 37.
Same page?
Yeah.
What page?
Oh no, on page 148.
Number 37.
Is this on 146 again?
148.
Dude, that was so fun.
Lucas, what do you think of Nick's warm up? This shirt's a good warm up.
Oh, I was wondering about that.
That was so
Yeah,
fun.
he wrote the AKA.
Yeah, so like, very, should practice, checks and tests.
Oh.
Oh, it wasn't bad.
Basically,
You choose.
sure it is.
Not bad. It's only hard because it's like.
Okay, I love problems like this, where it's not specific, it's totally general. These are good. So what's it saying here? As a spherical raindrop falls through a layer of dry air, it begins to evaporate at a rate proportional to its surface area. Show that the radius of the drop decreases at a constant rate. Well, first of all, this might sound kind of contrived, but this is the way it has to be. Think about, from where does a spherical raindrop, where is it going to lose its water?
in the air.
Yeah, outside.
Okay, but relative to the raindrop, say it again?
Yeah, outside.
Yeah, so the surface, right? So doesn't it have to be that way? As the raindrop falls through dry air and evaporates, it can only lose water molecules through its surface. And so the bigger the surface, the more water it loses, right? So that statement might seem like I'm telling you something that's specific to this problem, but no, that's what our intuition tells us it would have to be anyway. It has to lose volume. That's all evaporation is, right? It's losing the volume of water into the air. It has to lose water at a rate proportional to its surface area. Okay, has to be that way. I mean, there's some other things going on that we won't mess with. Maybe slightly tweak it. You know, as it evaporates, it's going to cool the raindrop, and so. But if we ignore that stuff, at the first level, this is how it would work. Okay, so we want to just show here. We want to prove that the radius of the drop is going to decrease at a constant rate. So first thing let's do is let's take this statement right here. Oops. Let's take that statement in blue and let's mathify it. We got to turn that into an equation. What did I do? Oh, whoops. You're right. I did. Ignore that apostrophe. Sorry. Okay, here we go. Listen. So how do we say that? How do we say proportional to? Equal to some constant times something, right? Where there's some unknown constant of proportionality. We don't know what that is. They didn't give us that, but it must not be important. So evaporate means lose water, right? Water is a three-dimensional thing, and so evaporating really is telling us V dot, isn't it? It's telling us the rate at which the volume of water is changing in the raindrop, right? As it evaporates, it's decreasing. So we can take this statement, and we could say then the rate of change of volume is equal to negative K surface area, right? So negative KS.
Wait.
K is just some constant of proportionality.
But I thought we knew the surface area of a sphere.
We do. We can plug that in. We do. You're right.
How do we know the surface area?
Well, because it's just in a book, or we remember it. What is the surface area?
Is it pi r squared?
No, that's the area of a circle. What's the surface area of a sphere?
4 pi r squared.
How do you guys know that?
Okay.
Does your brain PR
I'm actually. Is it 4 pi r squared? What did you say?
Yeah.
Okay, so
Where'd you go with the Oh, I knew.
right there. Okay, so
What's SSP? Is that SP?
Surface area of a sphere. Why
Did you get that? My gosh. Okay, so now that's one way of saying V dot, right? The rate of change of the volume. But what's the shape of this raindrop?
A sphere.
It's a sphere. So we could also start with the parent equation. V equals
Stop it.
4/3 pi r cubed, right? Hey, oh, watch. Shh, you gotta really watch this. You gotta really focus. You won't get this. And this is really, really cool.
Where did we get the, what's the parent equation?
Well, it's the parent equation because it's a spherical raindrop, right? We know that the volume of that raindrop is given by the equation 4/3 pi r cubed, right?
Yeah.
So we could-
that's surface area, that's fine.
Exactly, right. So there's volume
Of a sphere?
of a sphere, right? Okay, now we already had, let's just review this real quick. We were given this information about how it evaporates, which led us to this equation, right? Because the rate of change of volume is equal to, it's decreasing, so we'll say K is a positive constant, put a negative sign out front, because the V dot is negative, it's decreasing. V dot is proportional to, so it equals some constant times surface area, right? Okay, we can go back from just basic principles and say we know the volume of a sphere is 4/3 pi r cubed, then let's just implicitly differentiate with respect to t. What does that give us?
B dot.
B dot
V dot equals,
4 pi r squared.
4 pi r squared r dot.
Say pi dot.
okay, so if, would you agree, if that's v dot and that's v dot, by substitution, I could come up with the equation
Yeah, you can.
Ooh.
negative k times
It's our cube.
4 pi r squared equals 4 pi, gosh, this pen, 4 pi r squared r dot. Okay, but I could divide both sides by 4 pi r squared, right? And I come up with the equation then, r dot equals negative k. Well, what's k? It's a constant, right? So negative k is a negative constant. We just proved it, right? What were we supposed to prove?
Wait, how would you
That
prove
it
that
was
if you
negative.
didn't have the first equation?
Well, you couldn't, but we didn't need to be given the first equation, did we? We could surmise that because we know it's a spherical raindrop and the water's only lost through the surface, so it has to be true.
I thought we were just like finding a different way as well.
Start with
Like, using the volume.
Well, what we're really doing here is we're just kind of thinking about how the math tells us. I mean, there's some simple physics there, but really, just common sense tells us that because water is lost through the surface of the raindrop, we know that the rate of change of volume has to be proportional to surface area, right? We just can think that in our heads, and then we know what the volume of a sphere is, and so with just a little bit of calculus and very little stuff, we can show that by setting those two expressions for v dot equal to each other, we're left with the equation r dot equals negative k, which is telling us that the radius of the drop is decreasing at a constant rate. Because r dot is the rate of change of the radius, and it's equal to a negative constant.
So it's a negative constant.
Right. The negative sign, I just made k a positive constant so we could really point out that it's negative. Yes, Janelle, you have a question?
Why does the pi just like always carry like over? Why doesn't it get differentiated?
Because pi is a constant.
So
What's the derivative of a constant?
0.
0. Yeah. So remember what our rule is. Whenever we differentiate, we always just pull the constant out front and leave it there.
Okay.
Right. And that goes back, and let's just remember, if we go back to our derivative rules, we just said this. The derivative with respect to x of c times y is just c y prime, right? Okay?
Why wouldn't it be CY?
Rate that changes it.
We don't assume it, we just proved it. Right there. Right?
It's real hard. It's real hard.
Did you not think that was cool? I thought that was so cool.
That's awesome.
We could show that.
It means you wouldn't be enough.
What's that? That's right. That's what you have.